All right, ladies and gentlemen, so now we're going to move on to day 2 of 2.1, looking at standardized z-scores. The activity here is titled, How Did I Do? Again, this is an activity that you don't need our, any class data for in order to complete. So I recommend doing it. It's going to give you a better understanding of what standardizing our data does and why it's beneficial. So I would recommend doing the activity, or at the very least making sure that you're looking it over and looking at the key. Looking at some more formal definitions here in our notes, a z-score is a standardized measurement for each value of our data set. The way we calculate our z-score, or our standardized measurement, is x minus x bar divided by s sub x. Remember, x bar is the mean of your sample, and s sub x is the standard deviation of your sample. We can only do this if we know the mean and standard deviation. If we know the mean and standard deviation, and often with standard deviation I will shorthand that to an acronym of SD, and it's pretty common for many stats teachers to shorthand that to SD, just as a tidbit of information. So we can only do this if we know the mean and standard deviation of our data set. If we don't know that, then you can't standardize the score. But usually it's pretty easy to come up with those if the problem doesn't already present you with the mean and standard deviation. At its very bottom line, it simply tells you, what a z-score does is it simply tells you how many standard deviations you are above or below the mean. So if your z-score ends up being positive, then that means you're that many standard deviations above your mean. If your z-score is negative, then that means you're that many standard deviations below the mean. Remember, standard deviation is representing the typical distance a number is from the mean, your measure of center. So if you have a really big standard deviation, that means your data set is really spread out. If you have a small standard deviation, that means your data set is more smushed together. And so our z-scores tell us how many standard deviations above and below, because this is usually talking about real world problems, and to be exactly 1 or 2 or 3 standard deviations above or below the mean is not always realistic, and so this z-score allows us to be more specific with our information. So we're going to go through an example problem. Suppose a class had the following heart rates for students at a given time in beats per minute. So we have the following data points for heart rates. It says, suppose you are the student with a resting heart rate of 85, calculate your z-score. Well, before we can even begin any of the problems in this example, we need to come up with our x bar and our s sub x. So from chapter 1, we talked about how to use the 1var stats piece in a graphing calculator. If you don't have a graphing calculator and you have a school Chromebook, there's a graphing calculator on there for you. Or if you don't have that either, you don't have a school Chromebook, you could go to the Stacklet website, and that would calculate x bar and s sub x for you as well. There might be some other resources out there, but it's important that you're able to calculate these if you're at home, so you can begin going through these problems that we're about to go through from this chapter and on, okay? So, for the sake of time and this being a video, and my picture of me keeps going away. Okay, so what we're going to do now is I'm going to give you x bar and s sub x. So if you calculated this on your own, it should match my same numbers. But x bar, or our average or mean of this data, is 81.5. S sub x, or the standard deviation of this data, is 11.9. So now we're going to go through and calculate each of these z-scores. The formula for z-score is x minus x bar divided by s sub x. The X is referring to a specific data point. So the specific data point they give us in this first problem is a resting heart rate of 85. So 85 minus the average of 81.5 divided the standard deviation of 11.9. Now, if you're in habit of typing everything into a calculator all at once, that's fine, but you have to have parentheses around this numerator or else you're going to get the wrong answer. So here you should get a z-score of 0.29. All right, taking a look at the next one. Now you're a student with a resting heart rate of 72. Calculate your z-score. So 72 minus 81.5 divided by 11.9. And that's going to give you a z-score of negative 0.80. So notice that first one was 0.29 standard deviations above the mean. The second one was negative 0.8 standard deviations away from the mean or below the mean. You might be wondering, does it really matter if it's positive or negative? Yes, it does. All right, so the last one, and I know some of this is cut off on the video, but you should be able to have the notes in front of you. A student found their z-score in a certain data set of heart rates to be 1.12. If the standard deviation of the data set is 9 and the mean is 80, what is the student's heart rate? So a couple of things to note. They're telling us the z-score is 1.2. Then they're identifying the mean and the standard deviation for us. So if we're to use our z-score formula of z equals x minus x bar divided by s of x, we can fill in that z is 1.12. X we don't know, but we know x bar, the mean is 80, and s of x is 9. This is the most algebra we'll be doing in this class is in a problem like this. We need to solve for x. So using our inverse operations, the opposite of division is multiplication. So I'm going to multiply both sides by 9. That's going to give me 10.08 equaling x minus 80. And then I'm going to add 80 to both sides. And that's going to give me an answer of 90.08. We want to add a unit here. This number that we just calculated is talking about beats per minute. And that's it. All right, the next page. Remember, a z-score is simply a linear transformation of the data set. It changes the data set's mean and standard deviation, but not the shape. So if you did not do the activity, that's probably a really important piece that you were not aware of if you did not read through the activity, is that calculating a z-score or standardizing your whole data set is not going to change the shape. Okay, but it is going to change the mean and the standard deviation. The mean will then become 0 and your standard deviation will be positive or negative numbers. So, in fact, the mean for all z-scores of any data set will always be 0, and the standard deviation will always be 1. Below are the scores from an AP Stats quiz. We're going to go through this and calculate the median, mean, range, IQR, and standard deviation, and then we're going to go through some transformations. I recommend pausing the video and giving this a try on your own first and walking through these steps to see how the data points change before actually seeing the answers. So you should have paused the video and you should have gotten a median of 87.5 to represent the middle if we were to arrange these numbers from smallest to largest. The mean, or x bar, is 73.9. The range is 0 to 100, so if you subtract those or think about their difference, the range is 100. Interquartile range, doing Q3 minus Q1, is 90 minus 75, and we get 15. And standard deviation, S of x, is 31.7. Remember, using that one bar stats feature on a calculator will make this process very efficient for you. Now in the next box, we're going to take all of these original data points, the 95, the 90, the 95, the 65, so on and so forth, and we're going to add 4 to each of them and recalculate these key features. So if we do that, we get a new median of 91.5, a new mean of 77.9, the range is 100, the interquartile range is 15, and the standard deviation is 31.7. Notice things that changed and did not change. Now we're going to take those original data points and multiply them by 3 and recalculate these key features of the data. The median is 262.5, mean is 221.7, range is now 300, IQR is 45, and standard deviation is 95.1. Notice the things that changed or didn't change and by what. For this last box or table, we're going to take our data points, multiply them by 3, and then add 2 to each of them. Now we get a median of 264.5, a mean of 223.7, a range of 300, an interquartile range of 45, and a standard deviation of 95.1. Notice what changed and didn't change from our tables above. So now we want to summarize this, thinking about how the data was originally, and when we added a number, how those numbers changed, and when we multiplied by a number, how those numbers changed. So in general, the pattern that's happening here is anytime you have a median, it is always going to change by multiplying by B and adding A. Meaning, if you have a data set that's in 1 unit, say degrees Celsius, and you need to convert that into degrees Fahrenheit, you would multiply the original mean, or the original median by whatever that B factor is, and then add whatever your A constant number is. Your mean, you'd multiply by B and add A. Your range is only affected by the multiplication or the scale factors. Your interquartile range is also only affected by those scale factors. And your standard deviation is only affected by those scale factors. So if we think about transformations, if we're taking our whole data set and we're scaling it up or down by a number, all of these values are affected. If you're taking your data set and you're simply adding or subtracting a number, only the median and the mean, your measures of center, are affected. Your range, your interquartile range, and your standard deviation, your measures of variability, those are not affected if you're shifting all the data points backwards or forwards. All right, that is all for 2.1 day 2. Watch the next video for 2.2 day 1.